Unit 1 Chemistry, Chapter 3, Part 3, looking now at how we can modify the properties of metals. Because in their pure form, metals are not that useful. They tend to be either too soft or too reactive or too brittle, or just not what we're looking for. There are a few that we use. So when you put aluminium foil around your food, that is pure aluminium. If you look at electrical wire, that is pure copper. But normally we've modified them in some way. So there's a few ways we can modify them. We can make alloys, we can heat treat them, or we can coat them with something. So alloys first of all. Now an alloy is a mixture of two different elements, or sometimes more, but normally two. Okay? Because it's a mixture, it doesn't have a set compound, and it can be in any percentage that we want. Okay? Generally, the reason for making an alloy is to make it harder and to reduce the malleability. Okay? So something like a silver coil, silver coin, in which you need to keep the shape and you need to keep the embossing, you don't want it to be particularly malleable because you don't want to be passing the coins around and have them change. So the ones that we think are silver, there's no silver in them. They used to be way back when, probably not even in Australia, but they used to be. But now, 25% nickel, 75% copper. This is what we call a substitutional alloy. So if we look up here, these would be our copper atoms, or cations rather. And then here we'd have some nickel ones. They're pretty similar in size, and because they're both metals, they can both have their electrons being delocalized and going into this sea of electrons that just floats around. But because they're similar but not exactly the same size, these slightly bigger ones mean that the layers can't shift over each other. It's a bit like a speed bump kind of thing. So they try and push over each other, but they're unable to do so because it sticks out. Okay, that means that it's harder because it's more able to resist a force that you impose on it. And it also means that they don't change shape so easily, which we call less malleable. The other kind of alloy that we have are called interstitial alloys. Now this is normally a metal with some atoms of a non-metal thrown in there, quite often carbon. Okay, so here's our metallic lattice, and the blue is all our electrons which are delocalized around it. And then these little ones here are carbon atoms. Now as you can see, they're much smaller than the metal atoms, and they're fitting into the gaps. They're not going to metallically bond because they can't have delocalized electrons, but they can still stop the layers hiding over each other because it's like a physical barrier being in there. So again, we're making our alloy harder and less malleable. So if you get something like steel, stainless steel kind of thing, that your cutlery might be made out of, that's going to be mostly iron, 98% iron, but just a little 2% of carbon. Okay? This and the other one, they both have the same changing properties. What we would use is depending on exactly what other properties you're looking for in terms of their hardness, also in terms of cost and appearance and that kind of thing. Okay, so these are some common alloys and what is within them. Okay, so you might see bronze, for instance, which is copper and tin. Okay, that's very corrosion resistant and hard. So it's perfect for use out at sea where corrosion can be a real problem. You wouldn't want to use iron there because iron corrodes really easily. Okay. Now, the other way we can modify the properties of a metal is by changing the crystals within it. So this is an extreme close-up of a metal. Okay. When we're talking about those lattices, what we're actually talking about is the arrangement within a single crystal. So if you look at this, you've got these little lines. That's where one crystal joins another. So this is all one big metallic lattice. And this is one big metallic lattice. But here, where they join, that's not a metallic lattice. Well, that's just the join between the two. Okay? And the joins disrupt it. Now obviously the bigger the crystal, the fewer joins you have. Okay? And when you've got those joins, the layers can't slide over each other. So lots of little crystals means that it is harder, but it also makes it more brittle. It means that if you whack it with a hammer, it's likely to break into pieces. Okay? We can change the size and therefore the number of crystals by work hardening it. Okay, and also by heat treatment. So if we hammer it, then that's called working a metal, and that makes the crystals become smaller and becomes harder and more brittle. Yeah, if you get a paperclip and just bend it back and forth and back and forth and back and forth at the same point over and over again, you are work hardening it, and you will find eventually you make it so brittle that it breaks. The other way we can do is heat treatment. Now there's 3 different processes that we can use, which are called annealing, quenching and tempering. Okay? So if we do annealing, there our aim is to make bigger metal crystals. That's going to make it softer, that's going to mean we can draw it out into long wires. And to do that, we heat it to a moderate temperature, and then we cool it very slowly. And cooling slowly makes big crystals. The other one we can do, the opposite of that, is we can heat it to a moderate temperature, but we plunge it into water. And that makes a really hard metal, but it also makes it a little bit brittle. Okay, that's your classic, together with the hammering, that's the classic kind of medieval person making a sword, where you'll see them heat it up, bang it a few times with a hammer, plunge it into normally a barrel of water. Okay, and that's how you make your sword, because obviously you want the sword to be hard. You don't do it too much though, because otherwise it would end up brittle. Tempering is in between the two. So you take a metal which is already quenched, yeah, and then you heat it again, but not quite as hot, and you allow it to cool, but not quite as quickly. So you take some of these small crystals, and we're just trying to make them just a little bit bigger. So we heat them gently. Hopefully they'll merge together a little bit, and then we cool it a little bit more gently, so we end up with a nice hard but not quite so brittle one. Okay, and that's what your blacksmiths would be doing at the end. After they've made it very hard, they'll heat it, but then they'll leave it to cool out on the side. The final way in which we can modify the properties of these metals is we can coat them. Okay, now sometimes they coat themselves. If you take aluminium and you just leave it out in the air, it's going to make a barrier of aluminium oxide, which is going to stop the layer below from having a further reaction. And that's all good. But if you do start with something like iron, then you get rust which flakes off. And that means that the air can get to the metal underneath, which means it can corrode and eat away, and you end up with big holes eventually. So, in that case, what we do is we coat it. Pretty simple. Dip it in something. It could be a layer of a different metal, and that should say a thin layer, not a thick layer. Not quite sure what a thick layer would be. A thin layer of a different metal. Or you can paint it, or give it some other non-metallic protection, which might be like a rubber coating on the outside or something like that. Final thing we need to look at with metals is metallic nanomaterials. Now, nanomaterials, just in general, use things which are on the nanoscale. Nano is 10 to the negative 9. So 10 to the negative 9 of a meter. Right? Very, very, very small. Changes their properties a little bit. So this is someone wearing zinc sunscreen. This is also, on the other side, got zinc sunscreen, but with the nanoscale. Obviously it's not white, which has a better appearance. But if we look at it on a microscopic level, what we see is that the nano zinc oxide is actually better at reflecting UV rays away from the skin than the bigger particles. Okay? The bigger particles are more visible because they reflect more light back into your eyes that you can see, and rather than scattering it everywhere, which is why it looks white, but they let quite a bit of light through. Okay, so we see these bits of light going through, which means that ultimately you need to reapply it more often and you can still get damaged.